Hi guys, today I'm going to be teaching y'all Book 3, Proposition 14. The enunciation reads, in a circle, equal straight lines are equally distant from the center, and those which are equally distant from the center are equal to one another. So, first he gives us the circle ABCD, and I went ahead and drew that, so I'm going to put circle ABCD, and he also gives us these two lines which are equal to each other. So line AB is equal to line CD. So those are our givens. I hope y'all can see that. So what we're trying to prove is that line AB and line CD are both equally distant from the center point of the circle, which we're going to call E. So they're both equal. I'm going to say equally distant from point E, which is the center. Okay, so that's what we're trying to prove today. So, I'm going to move to this side. Okay, so our first step, we find the center of the circle, which is point E, and we can do that by using Book 3, Proposition 1. So we're going to say point E, center. And this proposition states that you can find the center of any circle. So we're going to call that point E right here. I'm just going to say it's right there. So point E. Okay. The next step he does is he draws a perpendicular line from E to AB. So he draws a perpendicular, so I'm just going to do that. And he calls this point F. So, and he uses Proposition 12, Book 1, which says that if you have an infinite straight line and a point off of that line, then you can draw a perpendicular to it. Okay, so we're going to say he draws line EF perpendicular to line AB. And he does the same thing and uses the same step and draws a perpendicular line from point E. I'm going to move that here. From point E to line CD. So he calls this point right here point G. So he draws EG perpendicular to line CD. His next step he uses is his reason is postulate 1, which says you can connect any 2 points with a line. So he connects AE and CE. So we're going to say line AE and line CE. Okay, next he uses Book 3, Proposition 3, which says that in a circle, if you have a line from the center that is bisected by a line not in the center, and it cuts at right angles, then this line is bisected. So he says that AF is equal to FB, and he also says that AB equals to double AF. So we're going to say 2AF, just like that. And then he does this other side the exact same way, and he uses the same proposition, Book 3, Proposition 3. And he says, oh, sorry, I don't know if y'all can see me. Okay. Then he says that CG equals GD, and then he says CD is equal to 2CG. So like this whole line is 2 of these, since those are equal. Okay, next, I'm gonna erase this because I don't have enough room. Okay, so step 7. Next, he pulls out these 2 triangles. So we're gonna pull out this triangle. Oh, that's rough. EFA. And then he pulls out this triangle, which is EGC. C. Okay, wow, that's rough. Okay, so then he pulls out these triangles and he says that the square on EG, this square right here is, so square on EG and then plus this square on EC or GC is equal to the square on EC. And he uses proposition 47. So proposition 47 says in right triangles, and we know that these are right here, that the sides subtending the right angle is equal to the sides containing the right angle. So the squares, so these two would equal that. And he does the same thing on the other side. So he says square EF plus square FA is equal to the square EA because of the same proposition. Book 1, proposition 47. Okay, then the next step, man, this is a small whiteboard. Okay. So then he says that this line right here, AF, is equal to this line, CG. We're gonna say because of statement 7 and 8. So line AF is equal to line CG. Okay, next he says the square on FE is equal to the square on EG for the same reason, because we already went over that. Okay, and then, oh, that was really good. Okay, and then he says that therefore that all of these are equal. That means that line EF is equal to line EG. Then he uses definition 4, book 3, which says that in a circle, if you have straight lines, they're said to be equally distant from the center because they're perpendicular, so they're equally distant. Okay, so we've proven 1, so we're gonna put a star by this. Yay, okay. Now I gotta erase it because I don't have enough room. 1 second. Okay, so next we're gonna prove, so we proved already that this line is equal to this line. Now we're gonna prove that AB is equal to CD. So we're gonna do what we did earlier. So we're gonna say line AB equals 2 of line AF's. So like 2 of those. And then we're gonna say line CD equals 2 of line CG's. And we said that earlier, but we're gonna put proposition 3, book 3. And then next he does something we've already done again. He says that the square on AE, so this square right here, is equal to the square on EC because of proposition 47. Because we know that AF is equal to GC and FE is equal to EG. So these lines are equal, and so those squares are equal. Next, he uses proposition 47 again and says that the square on FE plus the square on FA is going to equal the square on EA. And he does the same thing for the other triangle, proposition 47, and he says the square on EG plus the square on GC is going to equal the square on EC because of the same thing, proposition 47. Okay, so then he proves that all of these sides are equal. So if all of these sides in these triangles are equal, then that must mean that these lines, I totally screwed that up, that those lines are equal to one another. So AB, line AB, has to be equal to line DC. And that is exactly what we were trying to prove. So we're gonna say because of statement 12 and 13. Okay, so that's exactly what we're trying to prove. So we can conclude it with QED. Ta-da! Thank you for watching. Have a great day.